Welcome to today's Research Pays Off, and I'm going to hand it over to our speaker for today, Shree Rao.
Thank you, Lauren. Good afternoon, good morning, everyone. Lauren, I take it you can see my screen, correct? I mean, we're all set with the
Yes,
PowerPoint?
we can.
Okay.
Yes.
Um, so my name is Sri Rao. I'm with Applied Research Associates. I'm a principal engineer and associate at ARA, and I've been with ARA for 26 years and worked on several research projects, both for state DOTs and at the federal level. And this is a very interesting project for me. When I got involved in this, it was kind of eye-opening, some of the things that can happen with concrete pavements, and it's not like we're not unaware of potential distresses in concrete pavements, but this was kind of very interesting. So I hope you can look at this presentation and see that some new things that we probably saw that some of you may not have seen with your concrete pavements. I usually have an acknowledgement slide at the end of my presentation, but just in case I go over, I don't want to miss this important part of my presentation. Of course, I would like to acknowledge the National Road Research Alliance for the funding and the technical advisory panel that was established for this specific research project, who provided us with the guidance and also with the sections to be evaluated. Primarily the leader of the technical advisory panel, the chair, Peter Camp, from Wisconsin DOT, and then from Minnesota DOT, got a lot of support from Tom Burnham, the project manager, Maria Masson, Gordon Brune for some of the Minnesota sites, Illinois Tollway, where we collected some of the interesting pieces of information that are related to this cracking, and also the Federal Highway Administration. We borrowed their MIRA device for evaluating some of the test sections. This project, as the title suggests, is really phase one of a project, and there were three primary objectives of this project: to kind of look at some existing literature, develop some case studies of projects that exhibited cracking with dowel and tie bar related cracking. Look at what factors contribute to this kind of cracking, and propose some analytical and laboratory experiments to kind of further evaluate and come up with some solutions to mitigate this cracking. This phase one of the project is really focused on some field evaluation and the background information necessary for technically the phase two, which would be the analytical and laboratory experiments. So that part is not covered in phase one. That would potentially be a phase two topic, eventually funded by NRRA. So as I mentioned before, there's different tasks under this. We did a thorough literature review. We picked some case studies. In task two, we did field investigations, and we put together a field investigation report, a presentation, and the task 8 is this Research Pays Off webinar that we're doing right now. We're kind of wrapping up a memo for the analytical and lab experiments that could be done in phase 2, and we'll also put together a final report that basically combines the information that we collected and in all of these different tasks, and that will be the final report. So those all should be coming in the next few months and posted eventually. I would like to acknowledge the panel for providing us some of the site locations, and I'm not going to spend a whole lot of time. We really limited ourselves to 6 sites, and many of them were in Wisconsin, but also included the Illinois Tollway, Minnesota. But one thing I would like to kind of point out is these are not necessarily thin pavements. They are 10, 12-inch pavements with differing slab widths, different types of shoulders. But one thing that I do want to point out is these are relatively low age pavements. This cracking that we investigated in this project was on on pavements that were built not that long ago, and that's part of the big surprise of this type of cracking that we're evaluating. So the next 6 slides, I just want to give some feel for this type of cracking that we investigated in this project. And I'm going to go through these slides relatively quickly to kind of show the surface distress on this cracking. This particular one is on I-39 northbound in Dane County, Wisconsin. And you can see these cracks are pretty large cracks. And I think, at least from my experience looking at concrete pavements in the past, is sometimes we think anytime we see a joint distress, we pretty much automatically think one of two things. We think dowel alignment, or we may think it's related to durability because of moisture getting into the joints. But this looks a little different than some of those. So if you can see, these are kind of largish cracks, and some of them are more like transverse cracks that are close to the joint, and some of them are large spalls. And as you can see, some of these have been filled with asphalt. This one is in Columbia County. Again, there's kind of a pattern to these cracks. Eventually you kind of start seeing their spalls, and the depth of these cracks is another important thing. Some of these are not super deep. They're about half the thickness of the slab typically, and some of that will become a little bit more obvious as I go through the presentation. The third one, this one is on I-39 southbound Columbia County, and you can see again, there's this typical pattern of cracking that is near a joint or something like this. And then there's some other, the cracks might spread into wider areas, but this is kind of typical of some of this cracking. This one was from the Illinois Tollway, and this, of course, is from a vehicle-mounted camera that you can see this distress. Again, this is right at the leaf side of this joint, and you can see that crack that has extended pretty much the full lane here. And the same thing here. This is about half the lane. And just to be clear, this kind of cracking is not necessarily just limited to Wisconsin, although Wisconsin does have much more of this cracking than Minnesota and Illinois. But this particular one this may have some durability distress as well, as you can see there, but it definitely extends in Minnesota here on this particular project on Trunk Highway 610 and looks a little bit similar to the cracking I just showed in the previous slide. So, and then this one is in Eau Claire County, Wisconsin. Again, these largish kind of spalls that, and you can see here, is pretty widespread on some parts, on some slabs. So that's just to give you an idea for some of these crackings that are cracks that are near the joint, and they're potentially due to the dowel bar. But just to kind of summarize the surface distress and kind of talk about what we are looking at, there are relatively large spalls at transverse joints. They're relatively common in occurrence, with about 5 to 10% of joints that we looked at having this cracking after only 10 to 15 years of age, which is relatively young to see that kind of cracking, 1 foot or more in length. And I do want to emphasize that these don't look like durability related spalling. I know we do spend a lot of time talking about materials and durability of concrete, and there's a lot of good work that has been done in performance engineered mixtures and so on. But this doesn't look like durability cracking because of the extent and size of the cracks and their depth. Typically, the spalls are about half the depth of the concrete, and they lack any significant amount of hairline cracking. Often you see with durability type cracking, there's some hairline cracking around the spall concrete as the aggregates breaks the concrete matrix. We don't see that here. And then, so basically this initial information suggests that they may be related to the presence of steel, which could be dowel bars and tie bars in the concrete. These next 3 or 4 slides is from the Illinois Tollway. And what is interesting here is the progression of these spalls, and this one is taken from a downward facing camera on different joints, and there's 4 joints that I'll show. But this is 2018. There's a very small spall here. This is the same joint. It's again small, and then in a year or two, it's now become a pretty large spall. So it does progress relatively quickly, and another example of that is 2018 was a hairline crack. 2019, that crack has now become a little bit of a spall, and then by 2020, which is about 3 years, it's a major spall. So it's not a small spall; it's extended quite a bit into the longitudinal direction and in the transverse direction. And here's another example. This is again, these are different joints. 2018, nothing. 2019, we're starting to see a spall. 2020 is now a failure of the concrete. And here's another one. Again, the spall is small here, and here there's a patch here on this side. So clearly there was a spall here before, and you can see that patch here and the patch here, and then on the leaf side, it's getting extended. So just a quick review of this time history, at least based on this Illinois sections, is the spalls progress pretty rapidly from small to large, and they're not necessarily limited to approach or leaf side of the joint. From the information we saw, they're just as likely to occur on the leaf side of the joint as they are on the approach side of the joint. So the next series of slides, I'm going to show some interesting images from MIRA scan. For those of you who are not aware of MIRA scans, it's a little bit of a laborious process. It's ultrasonic device that you can see that's resting here on the concrete, and you basically move it along the joint, and then you can stitch these images together to get one large image for the full joint or the area that you're interested in collecting the information. So this is joint number 3 on I-94 at the Illinois Tollway. And here's, let me just clarify what we are seeing in this image, because some of the rest of the images I would, so you'll know what you're seeing. But this bottom line is right here where this mouse laser pointer is moving. That's just the reflection between the base and the concrete. So this gives you an idea of the thickness of the concrete. And these round circles, that's the reflection from the dowels. And you can see those, that's where the dowels are. And then right here, this is a crack. And oftentimes when you see a crack, the signal, it overpowers the base concrete signal, and the crack signal is stronger than this signal, and you won't see that. But when you don't have a crack there, you usually see a signal from the base concrete interface. So clearly here, there's a crack between these two dowel bars that is somewhere in this range. But the rest of the dowels look, the concrete looks pretty decent. So you can clearly see that here, there's a crack that's just showing up or just beginning to form or showing up, beginning to show up on the MIRA scan. So that's kind of interesting, but it's somewhere between these two dowels. This particular joint, and this is a 3D image of this same image. So this is 3D, this is 2D. And again, you can see that this is the interface between the slab and the base. And there's significant amount of cracking around the dowels. Now here, there's no cracking, so you can clearly see the signal between these dowels. The crack is now starting to form somewhere on here, and there's quite a bit of cracking at that dowel depth between somewhere in this range. You can see the cracks. What is interesting here in this particular image is that there is no crack on the surface. This crack is all subsurface cracking. So it's almost like a cancer of the concrete. You cannot see it, but it's there. There's a crack underneath there. Eventually, something is going to happen, and it will either show up as a distress on the top surface, or it might the crack might turn down and go into the base. Regardless, this concrete is not now fully, you cannot take full advantage of the full thickness of the concrete, because it's actually literally sliced into half, at least in some of these areas. And here's, like I said, a 3D image, and we're calling this delamination cracking. And this delamination is essentially at the dowel bar depth of this concrete. So again, this is kind of interesting images to see, and this image shows both the approach side of the slab and the leaf side of the slab. So you can see uh, the adjacent lane has some cracking, so clearly there was some which eventually turned into a spall, and you can see the patching here. But there was no cracking on the surface on either side of this joint, but underneath it, and again, just to kind of remind you, this circle kind of gives us some idea of the dowel bar depth, and so you can see that there's a crack, and then there's the dimensions in millimeters, so you can see that there's a crack. One thing I do want to say that not all the measurements are right at the dowel bar depth, and that somewhat makes sense because the cracks eventually turn up or turn down. So depending on how the crack progresses through the concrete, it could be higher or lower than the dowel bar depth as you go away from the joint. And you can see that in this case, there's not that much cracking here. These are the dowel bars, and then this half is cracked. What is interesting to me in this side is there's some amount of symmetry here, in the sense that there seems like there's cracking from here to here on both the approach and leaf sides, and then less cracking from here to here on both the approach and leaf sides. So there's a little bit of symmetry. Now, granted, there's some cracking here, and it's likely that some of this might eventually crack on this side as well. Here's another image, and again, this kind of is, you can see that there's a spall here, so clearly there was some kind of a cracking here. But on this side, you can see that we're now starting to see some subsurface cracking at that level. But from here to here, there was no cracking at the dowel bar depth level, so there's some cracking at that point. Here's another example of that. Again, there's no cracking on the surface, but there is cracking underneath the surface around the depth of the dowel bar as measured, as seen with this mirror scan. And there is cracking in the adjacent lane that had been spalled off and patched with asphalt there. Here's another one, cracking on the leaf side of this joint, and then no surface cracking on the approach side of this joint, but there is cracking, as we can see in this image, underneath. It just has not spalled yet. And here there's an image of a spall that you can see, and of course that spall, because the concrete is damaged, or because there's asphalt there, that image is empty there, and you can see there's a little bit of cracking underneath here and some cracking there. And I think I can skip through this one because it's similar image, but we also had similar images at a few other locations. This one is at Wisconsin, and again, it's the same. There is no surface cracking on this particular slide, on this particular image, but you can see that underneath the surface, it's significant amount of cracking that will likely eventually spall. Sometimes it doesn't spall to the surface. Sometimes it may just spall to the bottom of the slab and turn downwards, and you may never have a distress at the surface, but that could potentially lead to other structural distresses because you're not taking full advantage of the thickness of the concrete. And this was provided to us by MnDOT, but again, something similar here. There's a series of cracks extending from dowel bar to below at the depth of the dowel bar, and so this is again from an intact location, and it's also there at this project in Trunk Highway 610. So just a quick review of the information from the MIRA scans. There's a significant extent of delamination cracking beneath the surface that we may not necessarily see at the surface as a visible distress. Overall, it looks like they start around depth of the dowel bars, extend through multiple dowel bars, and in some cases, the full length of the joint. The cracking can be severe enough that the signals kind of overpower the signals from the slab-based interface, as I mentioned earlier. And both approach side and leave side of the joints have this cracking. And as I mentioned earlier, there's a little bit of symmetry. I wouldn't hang my hat on that and say that is definitely true, but it seems like when there's some damage on the approach side, let's say to half a slab, there's some damage to the leave side to about the same half of the slab. We did some coring also. This cores, and the next series of slides will look at the coring. You can see in this case, this core was taken about 27 inches away from the joint, the transverse joint. So this is the transverse joint. This is the lane shoulder joint. And this core was taken about 27 inches from there. You can see the crack formed. There are two images of the core. This is the leave side of the core. This is the approach side of the core. So it's just the same core, just flipped to the other side. And you can see it's relatively uniform in height or thickness. And so it's it kind of gives you an indication of how that crack is progressing underneath there. Again, if you look at this image, there's no crack on the surface, but this concrete is cracked literally in half underneath. This is the same core as this, and you can see in this case, this aggregate is went through the aggregate, which to me in this case suggests that this crack went through this point when the concrete was stronger than the aggregate, or the concrete and the aggregate may have had similar strength. Usually, if the concrete is much weaker, the crack might go around the aggregate, and you might have a whole aggregate piece rather than half an aggregate here. Now this, and part of the reason may be that this core is so far away from this joint. So by the time the crack may have progressed from the joint to the core, it was probably several years later, and the concrete had gained sufficient strength. This is a core that is a little bit closer to this joint. This is a different core, 9 inches from the joint, 47 inches from the from this edge, and in this case, you can see it's a little bit hard to see, but some of these aggregates are actually whole, and some of them are broken. So you can see there's an aggregate popped out here. So it may have gone around the aggregate. It's a little bit hard to say sometimes what is happening here with the cracking. This is, I think, the same joint as this one, and you can see we took the mirror scans at different distances from this joint. It's this is the scan as it looks on the image itself, and this scan is about 3 inches from this joint, maybe 4 inches. So, and you can see a clear crack underneath that scan. When we go further away, we're now here at about a foot away, and there is still that crack underneath the joint. And then on the right image, we're now about 2 feet away, and it's a little bit hard to see, but you can see these multiple signals, and where my laser pointer is pointing, that shows that there's still some cracking underneath. So the crack actually extends significantly away from the joint, and that somewhat makes sense if you look at this particular how this joint spalled. It spalled quite a bit. The way I envision this mechanism, and maybe I'm wrong about this, but I think what is happening is these dowels are causing some weakness, and there's going to be a plane of failure, and then the cracks eventually spread, migrate in this direction, and this direction, and this direction. And then eventually they turn up or down, and that could be due to the traffic action and just the loading action on it. But it's a very interesting distress that is being shown in these slides. I already talked about that. Here's a couple more cores. Again, This one is quite interesting again. If you look at, there's two cores, IC5 and IC4. IC4 is 35 inches from the joint. IC5 is 10 inches from the joint. Keep in mind, both of these cores were taken where there's no surface distresses at all. And all of this cracking is subsurface cracking in the concrete. And you can see IC5, which is closer to the joint, has the crack right about mid depth of the core, but IC4 has no cracking, and it's possible the crack hasn't progressed all the way to IC4 yet. But it's also possible that the crack kind of turned downwards, although the distance of about 2 feet from here, more likely it just hasn't progressed to that point yet, but it's possible it turned downward and went towards the base, and that's quite possible as well. But you can clearly see that there is a crack near the closer to the joint, and then as you get away from the joint, there's no cracks. This is Columbia County, Wisconsin coring. Again, this one was interesting. Again, this is a location that is probably about a little bit more than a foot away from this joint, and you can see the mirror scan clearly shows the cracking. The core crack here, to me, looks like it's lower than mid depth at this point. So, and that to me suggests that crack probably turned downwards into the base at this location. This is again Columbia County, Wisconsin coring. This core here was intact, and you can see that full core, but this core here was basically broken into two pieces. So again, to me, some of it could it's hard to speculate about everything, but it could be that this is a widened lane, and it could be the traffic loading here in the wheel path may be partially responsible, at least for the crack propagating through here, and not really propagating or extending to this core. It's a little bit hard to know for sure what's going on. We saw this in some other places as well, similar. And this is a core from Eau Claire County, again, roughly mid-depth of the core. In this case, is cracked. Again, some of it is hard to tell, but we have lots of this kind of evidence from coring that these cracks are about mid-depth. So just to kind of summarize the coring review, again, the report has more images, more discussions on some of this, but the cracks extend for several feet away from the transverse joint in the longitudinal direction. They extend beneath the concrete surface, even when there are no visible distresses on the surface. Seem to start around the mid-depth of the dowel bar, again, kind of confirming the coring and the mirror scan kind of go hand in hand, and they confirm each other. Eventually, I think the crack turns up or down. And this kind of, the cores taken closer to the joint generally have the cracks at the mid-depth, and then taken 2 or more feet away show the delamination crack either at mid-depth or higher or lower than mid-depth. Cores typically show crack progresses through the aggregate rather than around the aggregate, especially when the cores are away from the joint. But in some cases, the cores closer to the joint had cracks go around the aggregate. So I think some people may think, oh, well, it could be due to dowel misalignment, and I don't know if you guys can see this pop up. I'm trying to close that. There was a pop up on my screen, which from the Teams, and I just wanted to close that. We had some dowel alignment results from Wisconsin, and all these joints had very good dowel alignment. That's the basic summary of it, and I just pasted some images here. Very good alignment, and if you look at the distribution, over 90% of the joints had within plus or minus 2 inches translation. Over 90% of the joints had more than 5-inch concrete cover. In terms of misalignment, over 95, maybe even 99% were had less than 1 inch maximum misalignment, and over 85 to 90% had less than ½ inch maximum misalignment. And those of you who know about joint score, and I'm not going to get into the details of the joint score here, but joint score, over 90% of the joints had joint score less than 10, which means that the dowel alignment was very good at these joints. There was no issue with dowel alignment. So dowel alignment is not a cause for this cracking or dowel misalignment. We did obtain some trenching photos and images from both Wisconsin and Minnesota. This one is from Minnesota. You can see in this case, the crack extends right about mid-depth and pretty much the full width of this transverse joint. This one is from Wisconsin project. Again, it's a little hard to make out, but this is the dowel's depth, and the slab essentially is broken into 2 pieces. That's a better image of this is I-39, Blaine County in Wisconsin. Again, this photo was provided to us by Wisconsin DOT, and you can see the pretty much uniform crack right about mid-depth of the dowel bar. So the trenching operations, again, are consistent with the results from Core mirror scan. We did do some GPR testing at the Illinois Tollway, although it didn't give us that much useful information because it's a little bit hard to interpret some of the GPR images, but it is consistent with that as well. The lamination crackings are at the depth of the dowel bars, with again, consistent with all of the other information we saw. One thing I did want to kind of point out is these are pretty uniform cracks, suggest that the delamination action is caused by the combined action of multiple dowel bars acting in sync rather than that of 1 or 2 dowel bars. So and so it's, at the very least, to me, it likely indicates a horizontal zone of weakness for the crack tip to propagate. So that's kind of overall summary of the trenching. Now, it's interesting, once I started this project, I went through some file photos that I had from before, and I came across this couple of images, this one and this one. I believe one of these 2 is from Ohio. I'm not, I think US 24 in Ohio. I don't know which one of these is from that, but this phenomenon is not entirely limited to the upper Midwest, Wisconsin, Minnesota, Illinois, but it could even be Ohio. And I know I've had some conversations with some other folks in the concrete industry, and they may have seen this kind of cracking further east, Pennsylvania and New Jersey as well. Again, I think it is possible, and I can't say this for sure, but it is possible that sometimes we may be looking at this distress and thinking maybe it's durability cracking, but in reality, it is this type of delamination cracking. Now, one thing, so I'm going to kind of somewhat wrap up my presentation with a few other items and talk about some potential mechanisms for this cracking. And I came across this 1938 reference from Freeberg. And Freeberg, several of you may know that he did a lot of work on dowels and the Freeberg analysis you may have heard of in terms of how to incorporate dowels into your design procedure. But his lab experiments had something very similar to what we're seeing here. This is a direct quote from Freeberg from 1938. The initial visible distress of the concrete comes a considerable time before the ultimate load is reached. The initial warning almost always consisted of a small spalling underneath the dowel, first noticeable as a fan-shaped crack from 0.5 inch to 1.5 inch away from the dowel. In the deeper specimens, the first evidence would be a very small horizontal crack extending from the dowel toward each side, merging into a fan-shaped failure as the load increased. So it looked like Freeberg in his lab experiments saw something very similar to some of the items that we are seeing in the field on some of these test sections. And there's a couple of other references that kind of talk about this mechanism, and Rasmussen from Transtech and Makovich, they have some, Rasmussen especially, you can see that they talked about this, and I totally agree that this is probably the main likely mechanism by which this crack is happening. You have some curling of a slab, and then that is causing some weak zones under strain by the dowel bar. The weight of the slab also may play a factor in that, and then you have these stresses, and eventually the stresses result in some cracking, which then extends due to traffic load action, and either shows up as a spall, or a crack, or may not entirely show up, and it may just be a crack that's subsurface. So again, this is a potential mechanism, and so I think our best guess in terms of the mechanism for this cracking, at least from the phase 1 evaluation, is something like this. In the early ages, when concrete is just starting to gain strength and it's solidified, but it's just it's very low strength concrete. The strengths are pretty low, and then during this time, the concrete is vulnerable to high stress concentrations around dowel bars, and that may explain a little bit of why a lot of this is in northern Illinois / Wisconsin. It could be the construction time, and this. I think maybe Wisconsin, Minnesota, maybe Illinois have that significant swing in daytime and nighttime temperatures, especially in the fall and spring, and that significant swing in the daytime, nighttime temperatures probably is less common in some other parts of the country, and maybe it doesn't happen all the time, but that's could be a reason why it's a little bit more concentrated in this area. So then there's external loads due to these environmental factors like curling and warping, and then even there may be even some traffic contribution, such as early truck loading, and these loads may be restrained by the slab weight and dowels, and these restraint results in some stresses around the dowel bars, and the concrete may not be strong enough in this early age to handle these stresses. And so if these stresses exceed the local strengths, then you may have some micro cracks around the dowel bars. Eventually these, we don't see this right away. So the concrete now has gained sufficient strength, and the stresses are now lower than the strength. So the concrete looks okay, but then these micro cracks, due to traffic loading over years, kind of continue to deteriorate, and there may be some moisture impacts as well here, entering the joints and so on. And then due to the impact of the daily traffic loads and curling warping of the slabs, the daily moisture, everybody who's involved in concrete pavements is somewhat aware of the impact of loads and curling and warping on stresses in concrete. So they certainly probably exacerbate this situation. So eventually these micro cracks kind of coalesce to form cracks, and then they propagate horizontally and then turn upward and appear at the surface of the slab as a large spall. I think that's kind of what we're thinking is the mechanism for that. Obviously the factors that relate to this are concrete properties, how the strength gain happens, the modulus and early age factors during and immediately following construction, temperature fluctuations, difference between daytime, nighttime temperatures, which depends on the construction time of the year. And that difference is highest during spring and early spring and late fall. Curing may play a role in this. Of course, the dowel bar properties, the size, stiffness, friction between dowel bars and concrete, and then even slab-based friction probably has a factor in here, because if you have a significant amount of slab-based friction, then the concrete may not move as much if you have higher friction, and that may be beneficial as well. So some potential solutions, again, this is kind of very preliminary based on, because it's a phase 1 study and the limitations of this specific study, but look at the cold weather practices and see if you can reduce the likelihood of concrete placement where there is a potential for substantial temperature changes between daytime and nighttime temperature. Now, the dowel bars, again, I'm not sure how far you can go with this. Again, that requires some analytical and lab testing. You could potentially try using some less stiff dowel bars, reducing friction maybe by making sure or specifying. There was no way for us to do a postmortem on how properly dowel bars are lubricated and so on, but it could potentially play a factor in this cracking. Curing could play a factor to make sure satisfactory temperature and moisture conditions during early ages of setting and strength gain are adequate. This concrete strength is kind of a strange one. I think strength is always important for concrete, but because it allows the concrete to handle stress. However, sometimes higher strength concrete may mean less durable concrete. So you want to make sure you have durability. I mean, I'm not saying sacrifice durability. And so optimize gradation and things like that, that is needed for durability is very important. But within that framework of good durability, durable concrete, if you can get some higher strength concrete, it'll likely better handle stresses, but definitely not saying sacrifice durability. And so that's what I mean. However, there's a limit to how much strength can be increased. Higher concrete strength could be specified if and only if it meets all the specified durability requirements in a cost-effective manner. I mentioned the base friction. A stabilized base course would increase the friction, and that could reduce thermal movements and stresses in the concrete around dowel bars. And the same thing with coefficient of thermal expansion. Lower CTE can result in less thermal movement, or will result in less thermal movement, but it's hard to specify that because if you have a certain location for a project, shipping, if you are limited to certain types of aggregates, a little bit harder to specify CTE, but that may play a factor in some of this, but it may not be a practical, cost-effective option either. So a couple of slides. So phase 2, we're kind of putting together some potential things that can be done for lab testing, and just kind of find out what these factors and their relative contribution to cracking, and the testing matrix could include concrete mixtures, thicknesses, curing condition, a little bit harder to replicate in the lab. Dowel and tie bar types, simulated curling warping by changing support conditions. In the end, it's not the curling warping itself that is causing the problem. It really is just the stresses that are caused by that. And if you can replicate the stresses in the lab in a different manner, that basically does the same thing. And instead of spending a whole lot of money doing lab testing, you could certainly do some finite element analytical modeling to evaluate the stresses around dowel bars and to identify the factors so you can reduce your lab testing and come up with some parameters to evaluate in the lab based on the analytical modeling. But so that's kind of the last part of this project is we'll come up with some of these potential things that could be done in phase 2 to evaluate and further refine the mechanism and the factors that contribute to this cracking. So that's what I had for my presentation. So I appreciate all of you listening in to the presentation. We have a little bit of a time for question Q&A. So if anybody has any questions or comments, I'm certainly glad to answer.
Yeah, we do have a couple of questions and comments here in the chat. Pete had added a photo from Wisconsin about 20 minutes into your presentation, just I think for other folks to see. But Bernard had a question. could you shed more light on the extensive mid-depth transverse planar crack? We have observed it in many constructions in older concrete pavements. What mechanism is behind this?
I don't know when he asked that question, but I believe I may have covered some of that towards the end of my presentation. So Bernard, let me know if I did not answer that question, and if you want to add to that or.
Sure. Yeah. I know you were going through more mechanism topics during that point, so you may have covered it. And Bernard is welcome. Anyone's welcome to raise your hand or unmute to ask further questions. But I'll keep going here. So Tom had another question. Was there a correlation with dowel bar size? Thicker pavements typically have larger diameter, stiffer dowel bars. And did you see any issues with tie bars? Do you think modern mixes are more brittle? So it's a few questions there.
Yeah, I think the dowel bar size question is an important one. For the last several decades, we have been always saying use larger dowel bars because it reduces faulting compared to, and again, speaking in very broad terms here, you actually have to design a dowel bar specific to the, if you're doing an ME design or if you're doing, if you say, okay, greater than 10 inches, I'm going to use 1.5, less than 10, I'm going to use 1.25. I'm sure there's different things like that, but it's clear that larger dowel bars versus smaller dowel bars, the stress conditions are different, and that's where the analytical models are important. The larger dowel bars technically have less stresses around the dowel bars. All the models actually show less stress around dowel bars with larger dowel bars, but to me that may not fully answer the question. I think as a composite system, it is possible that the larger dowel bars may end up causing more restraint than smaller dowel bars. So I know I'm kind of going around the question because I don't know the answer here, but and that's where some analytical and some of that testing might be useful. But kind of to summarize, because the larger dowel bars have more contact area, they actually reduce the stress that individual bar has on the concrete itself. But we are talking about a composite action of multiple dowel bars, and that may be different because now you have more steel and more rigid steel in that composite section, and that may act differently. So we may have to look at it from a composite section perspective, not from an individual perspective. Lauren, you're muted.
Thank you. My computer's making some funny noises, so I had muted myself and I forgot. Thanks. I'm going to move on to Eab's question, and I see Bernard has his hand raised, so we'll get to that. So Eab said, something about your findings indicates there is a need to look at stress intensity factors and other fracture mechanics properties in the concrete around the dowel bars. The crack is initiating and propagating before the overall concrete strength is reached. Do you use fracture testing tools in concrete?
I think we should, and that may be part of the phase 2 analytical modeling, but that's not, yes, I mean, to answer your question, yes, that was not part of what phase 1 would be, but that would definitely be a way to incorporate some of those models in the analytical modeling, yeah.
And I do see that Bernard added to the chat that yes, you later answered his question, so I think okay. We got that covered. But Bernard, you still have your hand raised. Would you like to ask your question now?
Yes, my question becomes generic from the various things you have covered. Would you, in your reckoning right now, because the whole idea behind this is to look for ways of mitigating these phenomena that have been observed. Are you very comfortable right now with the way the aspect ratios we use for our various panels, the 4 to 15 footers and so on. I know that has minimized the concrete buckling in those days, which we were inundated with when we had very much longer panels. But the aspect ratio of the 12-foot wide lane versus the 15-foot and all that, are you satisfied that we have come to an optimum? Or do you think these are things we still need to look into with a variation of Poisson's ratios that we're observing in concrete, elastic modular that we're observing with new concretes, new cements all over the place, new pozzolan types all over the place? Is that an area you think are you comfortable with where we are with all that right now, or do you think that's a work in progress?
I think that's a work in progress because you're right. As the materials change, and particularly the modulus and the strength of the materials change, we may be in a situation where optimization may look different in, say, California versus Wisconsin and Minnesota versus Florida. I think they may be different ways to optimize it. But in the end, I'm an engineer at heart, and to me, engineer means one thing: cost, and everything else. If we had an ideal situation, we probably could build the perfect pavement, but cost it's always a balancing act to me between what does something cost versus what does something produce, you're in a situation where you have to evaluate the cost of doing something and whether it results in a performance benefit for that incremental cost. So I think there is room for optimization as we progress and as we have more knowledge on these mechanisms. I would also say that our knowledge is somewhat limited as well, and that's part of the problem. We're seeing some of these things. I think we are used to thinking of distresses in terms of let's say the MEPDG or something like that, and we're not focusing on the full picture of what causes failure in concrete, and all of those need to be combined and considered together as failure for concrete and optimized together, in my mind. It's a difficult, challenging problem, so I'm not saying it can be done within a few decades, maybe even, I don't know. But there's a lot of work to be done to understand these factors and mechanisms.
Thank you.
Okay, I would like to get through these other two comments in the chat, and then I see we have a couple of hands raised. So Pete said there may also be tie-in with joint activation. If the joints are not activating, then the contraction joint may propagate in the plane at dowel depth.
Yeah, and I agree with that. Joint activation is another part, and I know that Minnesota has done some work on that, but that may play a role in this distress as well. I agree with Pete. Yeah.
Okay, and then the last comment here from the chat is from Dulce. It seems to me that some of the spalling and cracking you saw could be due to lack of base support and not necessarily the use of dowel bars. As we know, dowels are very beneficial to reduce stresses at the transverse joints, so some may see your presentation and conclude that using dowels is not good.
I would never say that. So I hope I didn't spend an hour trying to convince people not to use dowel bars, because that's not the purpose of my presentation. So I apologize, Josie, if that's what you took out of this. Dowels are very important for concrete pavements. Let me start with that statement. And I probably should have started and ended with that statement. Dowels are, I think, in the history of the concrete pavements between 60s to current, the introduction of dowel bars are probably, to me, one of the most important aspects of the improved performance of concrete pavements, especially in terms of the right quality and faulting and all of that, pumping. And it's a very important part of concrete pavement. And I don't want to go into all the details and benefits of dowels. So that was not the purpose of my presentation. It's just that in some situations, and again, this is not, I wouldn't say this happens all the time. So in some situations this happens, and we just have to understand what are the factors and mechanisms that are causing this failure. The base, like I mentioned before, could be a contributing factor, but there's concrete that has been built with aggregate base all around the country, and they don't necessarily have this failure. So we need to understand this mechanism, and we need to understand how to select materials or make changes or do what it takes to reduce this cracking. But eliminating dowel bars would never be even in the top 100 recommendations that I would do for that.
All right, and then we'll go in order of the hands raised here. So Deepak was first.
Hi, Shreenath. Thank you for presentation. Can you hear me?
Yes.
Okay, good. Hey, we've been talking only about concrete. In my mind, I thought about dowel bars. So everybody knows, right? The coefficient of the steel is very high, right? So it doesn't only expand longitudinally, it could expand radially as well. So I see here mostly crack dowel bars very close to the joints. And when it's the deployed joints, you get direct contact with the surroundings. So it could be temperature could be changed so fast on the dowels, which is a really good conductor. And inside the concrete now there is a changes in temperature so much between concrete and steel. So do you think there is some additional contribution to stress due to radial expansion of dowel that will create a transverse cracking? That what you saw this?
I had not considered that, but I'm inclined to think that may not be a factor. And this is, again, I'm not saying it's not, because steel is a very good conductor relative to concrete, and the concrete, it is impacted by external factors, but the concrete has a certain temperature as well, and it is possible, but the steels, in my mind, should not expand to that extent to where it cracks the concrete. But I certainly appreciate the comment, and I'm a little. I need to think about that a little bit. Is it possible the steel is expanding? I don't think that is the case, because then we would see it in so many different places. But I am my feeling, having worked in this area for some time, is actually the curling and warping of the slab itself, and then the steel is trying to restrain that curling and warping, and that's what's causing the stress. But you may be right. I'll have to look into that. Yeah.
Thank you.
Thank you for the comment, Deepak. I'll certainly think about it more now that you brought it up.
All right, and then we have Iab had a question as well.
Shri, thank you. I would like to bring your attention to the MIRA scans, but first let me congratulate you for a very nice, well-organized project. You, your team, and the technical panel, and were delivered. My question is regarding the scans, the MIRA scans that you are showing. So I'm asking for your recommendation. When you don't have cracks on the surface, but they may be on the subsurface, how would you determine this is what the right time to do the testing? And then related to that, once you find out there is crack in the subsurface, how do you use that information? What kind of preventive maintenance do you feel recommending?
I think that's the biggest challenge, and that in and of itself is maybe completely you asked two different questions, and I'm gonna answer significant that, and you have all this cracking, to identify the location of this cracking. I do think the mirror scan does something very similar to that old technology of the chain drag. And I do think that the chain drag, of course, is maybe something that could be the first way of hearing and identifying a potential place where there might be a crack, and then you might use a mirror scan to kind of confirm that. And then you might identify these locations where you might have some distress. But I agree. I mean, it's hard to identify where this cracking might be. Let's say you have a project with 50 joints and they may only be at 10 joints, but it's hard to really know where it is, and it's hard to efficiently test for that. Now, maybe with GPR, we did do some GPR. You can start seeing that, but it would require an expert GPR analyst to look at each joint and kind of identify that. That's a potential way of doing that. In terms of maintenance, that's a difficult question. You know, the extent of these is so significant. It seems like full depth repairs are really the only tool we have to repair these at the joint. The problem is, if your joint is not failed, why would you want to do a full depth repair? You might as well wait till it starts failing and then do the full depth repair. I don't know if there's too many other tools we have for this extent of cracking.
Thank you.
Okay, I know we're a couple minutes over, but Pete has his hand raised as well.
Hi, morning still, everyone. To the first question Dulcie had, I know at least on one of the sections, we did some FWD testing and we had a very high subgrade modulus. I'm not sure about the base at this point. You know, somewhere in the 9,000 to 12,000. I don't remember right off the top of my head, but we had a very stable section. So I'm not sure the impact of a weak subgrade or base, but definitely would have some impact if you were trying to bridge something. The second thing is for identification of larger scoping of the extent of the delamination, we successfully used the impact echo from Cooper Engineering, I think it was, and they were able to map out a lot of the sections of delamination. Irregardless of knowing where those at, it's more of a reactionary fix where you do full depth replacement patching at areas that have come to the surface. I think long term, we've done a large patching job, and we're going to do an overlay, HMA overlay over the top of this just to kind of hold it in place until we can get a reconstruct. So that was all, just comments on some of the questions.
All right. Well, thank you. Any other last minute questions? Otherwise, we'll let you go and get back to your work days. Or in Shree's case, his vacation. I'm not seeing anything or hearing anything, so we will sign off for today. Oh, I see one more little comment from Bernard. In concrete reinforcements, true reinforcement occurs when stresses are shared by steel and concrete according to their modular ratios. This is not the case with dowels that transfer stresses by bearing action.
Yeah, but dowels are not technically reinforcement. So I think we use the word reinforcement pretty lightly, but dowels are, yeah, I agree with Bernard on that, yeah. All
right. Well, thank you very much, everyone, for attending. And Shree, thank you for your presentation. This will be uploaded to our YouTube channel by the end of the week, Thursday or Friday. So if you want to come back and review the questions or any of the content, it will be available there. Thank you, everyone.
Thank you very much. Thank you, everyone. Bye-bye.